Okay, so let's start with knowledge graph building with the Smart Graph framework. The following presentation gives you an overview of that framework, specifically its layer architecture, which you see here. So when you're dealing with knowledge graph, a key thing is always getting the data. I mean, we are not, creating out of the blue. We are using data to collect, to create our knowledge graphs from. And of course, the better the quality of the data, the better our knowledge graphs will be. We do this through backend connectors. The backend connectors have two sort of basic tasks. They know about the structure of data sources, because this structure also contains knowledge graph information, as you will see. And secondly, it provides us with the content, within these sources, so that, further methods can be applied to this content. In general, there is, if anybody tells you there's a single method to create a knowledge graph, this person will be wrong. There is not, and most likely there will never be. So knowledge graph construction requires the orchestration of a number of computational linguistics methods. For us, in the center of that is semantic information extraction. We're doing this with so-called unification grammars. Later on, what that exactly is. But of course, we are also using LLMs. We are using external RDF resources, and we are concerting all of that under a scheme of truth maintenance, so that whatever we add to the knowledge graph is checked for, does it improve the knowledge graph? Does it add reasonable information? And, once we have one, we make it persistent. There is a standard for knowledge graphs called Resource Description Framework, and it's an XML standard. So there's also a schema for that, which is called RDFS, and schema standard to be exact. And RDF and RDFS provide for a number of output formats for knowledge graphs. So you'll see that some of these make a lot of sense when you are working with complex knowledge graphs. And finally, when we have created a knowledge graph, then we can navigate through it. We can update it through new information. We can analyze its statistical information, and we can use it to prompt language models, which is, I guess, a thing many of you would be interested to do. Who would like to prompt an LLM with knowledge graph information? Who finds that an interesting concept? Yes, I think you also do. I should add that it's not the only way to combine knowledge graphs and large or smaller language models. You also can fine-tune a model with knowledge graph information. That's something we don't do that much. but for the sake of completeness, it should be added that this is also a viable method. Knowledge graphs and LLM is a very active research field, and so there are many ways to happiness in that field at the moment. Okay, how do we construct a knowledge graph? Well, you saw already the layered architecture. We cover both the structured and the unstructured information in our backends, very importantly. Many people do only the structured one and are missing a lot of information. We try to minimize human intervention, but there are cases where there is not much semantics, and where you need to do some knowledge engineering, as it's called. You need to sit together with clients and ask them, what is this, what is that, what property does this component have, and so on. Write it down and then bring it into the knowledge graph. So that's manual knowledge engineering, and we also support that. We are using various rule-based control mechanisms. You will learn about them later on. All that can be done through REST APIs. So it's easy to use in whatever application you are building. Note that all that is based on RDF and RDF schema. That's not the only standard. Another important one is OL 2 to be exact, for the ontology description. So in a knowledge graph, strictly speaking, a knowledge graph does not need to have a type system, but OL provides you with standards for typesetting, for developing an ontology-based type system, and our knowledge graph always do have built-in and custom types. That's how a knowledge graph looks like. So essentially, you can think of a knowledge graph as a huge set of statements, each statement consisting of subject, property, and object. And so the property can be depicted as a link between two entities. There are two things to observe here. First, objects may be classes of entities, and an entity typically is a specific object of the real world. Like it's a name of a company, it's or a person, it's a measure like degrees Celsius, or it's and in Wikidata, for instance, they have the concept of the QID, and the QID is always represented through a URL. So think of a knowledge graph entity as an object represented in the outer world, so that you can point with a URL to it. One important aspect of knowledge graphs is so-called reification. What is that? Reification is that a statement in a knowledge graph is itself a knowledge graph entity, so that you can refer to other statements from the knowledge graph, and in that way build complex logical structures. Reification is what brings you the power of knowledge graph description, and you will later see how we make use of the reification concept in our knowledge graph construction. So we have quite a few connectors, the important thing is that all the connectors for the various backend sources have a specific interface to knowledge graph builders. The builders add physically statements to the knowledge graph, and the connectors are specific for individual sources. And you know, when you have a specific client's needs, you can add a connector relatively conveniently. As I said, we have a number of computational linguistics methods, these methods, you know, they are abstraction methods. They try to find abstractions within the data and represent them as knowledge graph triples, statement triples. The term statement and triple is often used interchangeably for subject, property, object structures. The purpose of computational linguistics methods is to build such statements as reliably as possible. Knowledge graphs are built under a precision-oriented regime. So we are trying to have only true statements in our knowledge graph. If we are not sure, or if something is doubtful, then it's not a good knowledge graph statement. You know, if the knowledge graph doesn't, you know, is not true, then it's maybe better to resort to what's in the LLM anyway. Our knowledge graphs and knowledge graphs in general maybe live in main memory. Of course, they can be exported, saved in many ways. The important thing is knowledge graph building is computationally expensive because you need to access existing statements all the time. You know, we have our internal representation for knowledge graphs. In the literature, you will often see SparkQL being mentioned, which is the RDF query language originating from the semantic web movement. SparkQL is very powerful, but it is has been developed with a database, you know, relational database concept in mind. And from at least my point of view, it's not ideal for LLM querying, where you do not necessarily have that database perspective. And SparkQL tends to be quite computationally expensive. We provide all the functionality through a REST API with a lot of project types. The project types help you to organize your application around certain functional foci. As you will see, the REST API provides, you know, anything you need for building a knowledge graph, including a lot of statistics and differences between knowledge graphs, of course, querying, augmenting, and so on. You know, it's quite powerful, and we are extending extending it continuously. So here you see our build workflow in all its beauty. On the left side, there is the document extraction. So we're currently supporting doc files, PDF, and XML type of documents. The way we do that is we are using an XML schema to sort of build XML documents from these documents. Why? Because XML documents are a first step towards a defined semantics. In knowledge graph building, everything is about semantics definition. With XML documents, CSVs, databases, and various other types of sources, we have mappings, and the mappings guide the connectors in extracting from this type of data. So essentially, the mapping tells the connector how to interpret a certain element in delivered through a connector. So both the XML schema and the mappings for the various sources, these are your primary sort of rule sets to deal with content in knowledge graph building. You will see later on how that works in detail. So choosing the right mappings here and the right XML schema is like designing your knowledge graph so that it does what it should do. All the information from the connectors goes into the knowledge graph builders. Cruise maintenance playing a big role. And the other thing that works on knowledge graph is the so-called builders, the sort of method-oriented builders. So we have tau extraction, which is the tau language is our semantics language, and we are building tau statements with a unification grammar. Building unification grammars is a sort of advanced subject, which we will not go deeply into in this workshop. If you're interested to learn it, you're very welcome to, join us and, But of course, at Textverstehen, we do have a lot of grammars, and for many customer situations, we can just take a grammar out of a drawer that will work for the content in question. Other builders use large language models. So we are using LLMs to extend knowledge graphs in special ways, and of course, RDF and RDFS sources, for instance, Wikidata, of course, is a huge knowledge graph, if you will, essentially developed out of Wikipedia. You can think of Wikidata as a knowledge graph of the Wikipedia content. That plays a role in the semantic web movement. And we're using these well-curated resources to sort of add to our knowledge graphs. Yeah, that's it for now. Any questions on that? In the online session, any questions?
I do have one question.
Yes, please.
When you're building this, where does the most effort go into? Like, what's the hardest thing to develop to make a useful graph builder?
The hardest part is, of course, is setting up the mappings correctly, and also the unification grammar, setting it up correctly. That's the hardest part, I would say. So unification grammars, they consist of rules and dictionary, and that controls to a large extent how good the content extraction in your KG will be.
How well will the text be actually interpreted versus like compared to human, right?
Yes. Merge graphs are not made for extracting all subtleties of semantic content, but they are meant for grasping the key relationships between entities.
Which is the big difference to regular databases. Regular database stores information, and knowledge graphs introduces the relationship between information.
Yes, you might say that databases contain a lot of information, but very limited semantics.
Exactly.
So what semantics do you have in a database? Maybe table names and column names, but that's usually not enough.
One question from me,
Sure.
You said the mappings are a huge part of developing a knowledge graph. Is you have to do, for example, for each database or table, own database mapping you want to integrate into it? What does it mean by a lot of work is done with mapping part? So if you, for example, you want to integrate 3 databases or tables from different databases into the knowledge graph, so you have to make for each database
so
own mapping.
So far, you would provide a mapping for each table. That's very true.
Okay.
And
So and in the mapping there is some semantics of
yes.
Okay.
The mapping is essentially how.
What is the data?
How
Description basically.
What is to be made of the cells in the table, right? In terms of knowledge graph entities, and in terms of the internal knowledge graph type system. And you'll see that. Okay. Any more questions? Is there something in the chat?
No, not yet.
Okay. Then I would propose 5 minutes break, and we continue at 1:45.